Now I will go over this example from the book. It is example 6-9. It's an example about a beam design and a girder design considering bending, shear and deflection. Okay, let us see the example first. What it says, it says a floor plan. It's a floor plan, that means not roof, is floor. Design members B1 means this beam, and G1 girder, this girder, for bending, shear and deflection. Compare the deflection with L over 240 for total loads, L over 360 for live loads. That is the deflection criterion for live loads. This is the deflection criterion for total loads, that means live load plus dead load. The material is ASTM A992 grade 50, that means yield stress is 50 KSI. Assume CB is 1. Now you know what is CB. CB means moment gradient factor. We need it for bending design for beam. Okay, we will see dead load including beam weight. That is important to know. Does it include beam weight or no? So this dead load includes beam weight is assumed to be 85 psf. Now if it doesn't say that, then you can assume some weight of the beam and then later on check whatever that is section you are getting is okay or no. So at the beginning better to assume a higher beam weight, but good news, this time they told us this dead load includes beam weight. Then the live load is 150 psf. 150 psf, good. The floor deck provides full lateral stability. That means when we design for bending, the beam will not have any lateral buckling. What does it mean? Full lateral stability means no lateral buckling. LB, laterally unsupported length, is 0. So it is important to know full lateral stability. Now it is for flange B here. Now what is happening? There is a deck here, deck that means floor. There is a floor here that will be tied to the beam so that the beam cannot have lateral buckling this way. But what about the girder? They did not tell anything. That means this beam and this beam will provide lateral support here. This beam and this beam will provide lateral support here. So for girder, the laterally unsupported length is this. That means the LB for girder is 6 feet 8 inches, but the LB for beam is 0 because it's fully laterally supported. Okay, hopefully you understood. Ignore live load reduction. That means whatever the load given, live load how much? 150. We cannot decrease it. The problem is telling do not decrease it. Use the design table AICM where appropriate. That means we can use the AIC manual. Okay, so we will start the design. We learned everything, and make sure that before starting this example you saw the video about design for bending, design for shear and design for deflection of steel beam. Now when we will design the beam, again our first step of designing a beam or whatever, we need to finalize our load. This load is raw load. Raw means not processed. So when you design the beam, we need a load on uniformly distributed load on this beam. But this beam is in PSF. That means this way versus this way. So we should multiply by the tributary width of this beam. Tributary width means 50% this side and 50% that side, but both sides same length. So my tributary width here is 3 feet 4 inches. 3 feet 4 inches here. That is the tributary width for this beam. We will multiply this tributary width with this load. But again, before this, this load is not factored. So we know that there is a topic factoring versus non-factoring. We'll discuss. Okay, maybe now. When we design for deflection, we do not factor the load. We use the service load. When we design for shear and bending, we use the factored load. That means we need to factor this load by the load combination. Even we can memorize when there is only dead load and only live load, the factor is 1.2 here, 1.6 here. We can memorize this. It is combination number 2. Okay, that is very old story. If you forget, you can go back to the load combination and see the factoring rule. Okay, so we learned about the tributary width here. What about the load in this girder? Now many approaches, whatever. Okay, before opening the solution, let me discuss something here. What is the load here? So the load here is a two concentrated load. One is one here, one is one there. What is the value of this load? Whatever the support reaction of this beam here, and whatever the support reaction of this beam here. Now this span, load is same. So whatever the support reaction here for this beam times 2, that is the concentrated load here. Same thing here. Whatever the support reaction for this beam here plus support reaction here, combination will be a concentrated load here. That is one approach. I followed in this style. Your book followed other style. What is that other style? Your book, what it did, the concentrated load here will be 50% here to 50. That means 50% this side to 50% this side, 50% that side, that's up to this, and then 50% that side. The percent means whatever the total length, half. That means the load here will be the combined load from here to here to here to here. That means this will be our tributary area for this load or for this girder. That means the tributary area for this load will be this side 15 feet, this side 15 feet, this side 3 feet 4 inch, that side 3.4 inch. That is another approach to calculate. Whatever approach you follow, whatever common sense you have, you can use your own common sense to find the load here. Okay, now we'll go to the solution. Okay, so first what they did, they summarize the load. First is PS. PS means load in surface. S means surface. So load, it is P means pressure, the applied load. So 85 PSF, sorry, KSF, dead load, live load. They added together, and that is the it's PSF. PSF total is PSF. Then they divided by 1000. It became KSF, kip per square feet. That is the total service load. Then they did the factoring 1.2, 1.6. It is the factoring load combination number 2, and they found this combined load, and then it is in KSF, kip per square feet. Now this is factored load, this is service load. Why do we do service load? When we will design for deflection. Deflection design is based on service load. Why? Because deflection is not a structural criteria. It is just a aesthetic criteria. That means beam will not fail, but it looks odd or ugly if deflection is so big. People do not like it. So this is why we do not put so much safety in the deflection. Okay, now go to the beam. First tributary width, you know why it is 6 feet 8 inch. So if I do here again, this is my short plan view. I put it here so that we need it per B on 3 feet 4 inch this side, 3.4 feet that side. Total is 6.8 inch. That means 6.67 feet. This is feet tributary width, and that is my service load. We saw 0.235 service load. Then total is 1.57 kip per feet. That means in this beam 1.57 kip per feet is my service load. And then what is factored? Again multiply the tributary width, then my factored load, this one, then this becomes 2.28 kip per feet. This is factored load. Okay, then what is my maximum shear force? WL by 2 for a uniformly distributed load. The support reaction is WL by 2, and that is the maximum shear force for a uniformly distributed load. We know that from our previous classes, say statics, strength of materials, structural analysis, whatever class you did, that's good, and you saw that how to find this. Now if you do not know how to find this, no problem, draw the shear force diagram, draw the moment diagram, you will find the maximum shear force, maximum moment. But I advise you to memorize at least one beam, that is uniformly distributed beam. The maximum reaction of a uniformly distributed beam is WL by 2, and that is the maximum shear force, that is the maximum reaction, both same. The maximum moment of a uniformly distributed load is W L square by 8. And maximum deflection, we do not need it here, but still to memorize 5 W L to the power 4 divided by 384 EI. Better to memorize that. It will help your life a lot. So we got our maximum shear force, maximum moment for the beam. Girder, yes. How did they find the service load? Again, your book approaches this 47 is only the load here. So here tributary area 200 times why 200 is 30 times 6 feet 8 inch. 6 feet 8 inch means 6.67 feet is 200. How it is that? So 3 feet 4 inch this side, 3 feet 4 inch this side, 15 feet this side, 15 feet that side. Total area is 200. Multiply by this 47 keep. So this 47 keep is load here. That means here. And if we use the factor load, we'll get 68. 68 is factor load. That means load here is 68 if it is factored. Load here is 47 if it is service. So we got both loads. Now I told you earlier that the concentrated load here will be whatever the reaction here plus whatever the reaction here. As it is symmetric this side and this side, whatever the reaction here times 2. Let us see what is that. Reaction here is V max 34.2. That means reaction here 34.2. It will be double because from both side, on side, and 34.2 times 2 is 68.4, and they got 68.4. Same thing. Whatever approach you use is same. So what we did here, we just calculated the load, nothing else. Oh, also we calculated the maximum shear force, maximum moment. Same thing for here. Why the maximum shear force is this? Yes, because 50. That means it's symmetric beam. Whatever the load here, that will go here. Whatever the load here, that will go here. That means the two support will share the load equally because it is symmetric. What is the maximum moment? PL by 3. Now this is the equation we know for a third point loading. Third point means on, second, third. If I divide the beam into 3 equal segments, that is called third point loading. For third point loading, maximum moment is PL by 3. Now if you do not believe it or if you do not like it, no problem, solve it. The maximum moment of this beam will be at the middle because symmetric, at the middle. Then support action times this distance, which is 10 feet, minus this load times this distance. Then you will get this moment. Simply, if you know the equation to find maximum shear force and maximum moment is good, use that equation. If you do not know it, then solve the beam. Draw the shear force diagram, draw the moment diagram, take the maximum one. And you, by this time you know how to do it. So all of my force, shear force, deflection now known. Now we will start design. They started design using moment. Now there is no universal way to design. There is no universal way to there is no universal sequence to design. That means you can start designing with moment, then check for shear, check for deflection, or you can start design using deflection, then check for moment, check for shear, or you can start design with shear, check for moment, check for deflection. Everything is okay. I prefer to start design starting with deflection. That is easier to me. Okay, so now we are designing beam. We know our maximum moment, we know our LB, because we know that the design capacity of a beam for bending depends on the laterally unsupported length. So this length LB is 0. So what is the capacity of this beam? From the AISC manual, if LB is 0 or LB is smaller than or equal to LP, then the design capacity is PMP. It is not given here, but we know that. Okay, so what they did, they went to the ASC manual table 3-10. Now this number may change with the edition of the manual. So, or whatever edition you use, just find a section whose PMP, that means PMP, not N. N is the capacity, and that value is PMP. We know that. So from the manual, find a section which can take this moment. Simply, that is the rule. So we went to the beam and we saw a section this, and that section can take 274, greater than this. So looks good. And if we explore the AIC manual, you found that another beam 1840, that means same load, same self weight, but larger section. It can take how much? 294. So even better. So same dead load, but my capacity is higher, so better. uh, and more stiffness. More stiffness means higher I value. So here we are getting 518. Oh, last time for this section we got 518, and for this section we got 612. That means compared to these two sections, this section is better. Okay, they initially selected this section. No, that is not the final, it's just initially selected for bending. So bending design is done. Now this time very easy because our LB is very small. If LB has a higher value, that means some length, then whatever you learn for the bending design, you will assume a section and check that section whether it can take this amount of bending or no. Okay, so bending design is done. Then when we are designing for deflection, I required WL to the power 4 by 64. You saw this equation when you saw the video or article for design for deflection. It is the equation for the I required. WL to the power 4, 64.44. W means again service load. This should be service load in linear feet. So what is 1.5? If I go back, you can see here the service load 1.5. Do not by mistake use this one for deflection. Deflection uses service load. So then they found they need 658 inch to the power 4 I value. Whatever section you used, it had 612. That means it is not good for deflection. Good for bending, but not good for deflection. So they went to the book again and found that this section is not good. So they took a larger one. So they tried different section: 1650, 1846, 2144, 2455, and they found that all of them has higher I value than the required. What is the required? Required I value 658. 658. So all of them have it, but which one is better to use? This one. Why? Because it has a less or lighter section. It has less self weight, 44 pound per feet. Now you can choose any section, it's up to you, but this has more technical power. That means it is lighter, but or lightest among all them, and it has a greater I value. So this is a good section, but at the same time this section is higher depth compared to these two. So selecting a section is a challenge. It depends on the self weight and architect's opinion also. Architect always likes lighter, smaller section. So maybe an architect will like this section. A civil engineer will like this section. So it's bargaining. Okay, whatever it is, you hopefully will learn what I mean. So we selected this section because it is lightest. Now we have to check whether this section is better for the moment or no. But typically a larger section will be obviously better for moment also, and they check that from the AIC manual this section can take 358 cubic feet, which is even larger than our maximum moment. So it is good, and it will be obviously good. A larger section will have larger moment capacity also. Then we did that. Then for checking for shear, we know that this is our shear equation, and in shear equation we need a phi b cb. Now this t value, if the ASC manual doesn't show any superscript V. That means if you find this section in your manual chapter 1, which is in my current manual, I have 15th edition, I can find page number 1-18, this section 2144. Oh no, I didn't find it. This section 2144, yeah, 2144, yeah, 2144. This section does not have a cylinder wave. How? There is no superscript V. This V will be in the superscript. If on the top of 44, if you see a V, that means this value is not on. But luckily there is no superscript V, so CB, PB both are 1. So P 1, 0.6, FY 50 KSI, because it's the 50 grade steel. AW TW times D. This is D depth, TW thickness of the wave. CB is 1. Now again, why CB is 1? In chapter 1, after 44 here, there is no superscript V. That means it is not a cylinder. It doesn't have a cylinder wave. So these two values are 1. Then we found the capacity 217. What is our shear force? Only 34. That means this section is good for shear. So what we did here, we started the design with bending. We took a section. When we checked for deflection, it did not satisfy. Then we increased the section, and then for the increased section, we checked the moment. It was good. We checked it for the shear. It is good. So beam design is done. Okay, then we will do the girder design. For girder design, we know the maximum factor moment. LV 6.67 feet. Why? Let's go back. You can see here. Okay, even go back. There's beam here, lateral support, beam here, lateral support. This problem did not tell whether the deck on top of this will provide lateral support throughout the beam girder or no. If the deck provides lateral support throughout the whole girder, then LB is 0. The problem did not tell anything. That means the lateral support is only here and only here. So our LB is this or this or this, whatever. Okay, so go back. So you know why it is LB is this. So, yeah, so LB is 6.67. Now we went to the table 3-10. We found a section. It can take this amount of load. Now you should check whether the LP is greater than this or no. If it is greater than this, then good. If LB is greater than LP, then you have to use the equation to find the capacity. Again, it takes a lot of time, and you know what to do from your bending design. You have to compare this LB and LP. So if I open this section in the manual, which section? 2455. 2455. Yeah, 2455. I found this in my ASC manual. I found a table 3-6. Again, in my book, this is not 3-10, it is 3-6 in 15th edition of ASC manual, page number 3-55. In that page 2455, the LP is 4.73. LP is 4-73. That means my LB is greater than LB. What about LR? LR, I see that, if I am reading right, 13.9. That means my value is in between. Then what is the capacity? Capacity, they found 460. Now 460, it is not directly available in the manual. You have to calculate it. That means you learn from bending. Here I do not have any tool, but if I open, say, a pen to show you what you need to do. So here what is happening, okay, write it down. Okay, LB 6.67 and LP I found from book, it is 4-73. So what is my moment equation? Let me, whether I can write it here, which one. So my capacity will be CB time P M P, then if I can remember correctly, P B F, then L B minus L P, and the whole thing must be smaller than P MP. Now you have to use this equation to get this which number, to get 460. Now okay, let me do very quickly if I can do. What is my CB? Okay, it depends on the lateral support. Lateral support, if I open your book very quickly, so CB, yes, here from this lateral support, yes, here lateral support at the third point. So my maximum value is 1.67. this is 1 here. My maximum moment is here, so I should use 1. So CB is 1 because my maximum moment is here. Okay, so it is done. At least we got one value so far. Yes, it is taking time. Hopefully you will be with me. So CB is 1. Okay, discard CB. What is MP? From the manual I found MP, it is 503. Whenever there is a rush I make mistake, so hopefully you understood what I am doing. So it is 503 from their book. What is BFF from the book? For this section 24-55, PBF I found 14.7. 14.7, so there is a point here, and then LB is 6.67 minus, what is my LP? LP is 4.63, sorry, 4.73. So let me check quickly. 503 minus 14.7 times 6.67 minus 4.73. I got 474. And how much they got? They got 460. Now why there is this 24? Yes, I'm reading the right section. So 24.55, they found 460. I do not see any 460 here. So yeah, any mistake so far I do not see. 4.73, 6.67 and 14.7, 503, and I use here 1. Yeah, I do not think, I do not see any mistake here. So maybe when I pressed it, I pressed something wrong, but again no, it is right. Okay, we will go about this. So I found how much I forgot it, most probably 474. Again, maybe I made some calculation mistake, or but that is the approach. uh, or even sometimes with addition, some value changes a little bit, the capacity, the coefficient. So it should be okay. Maybe they use the very older version and we are using very new version, so every time coefficient changes, so that is okay. Coefficient means p, uh, and this value it changes little bit. So maybe this is why the it is not matching. I'm getting 474, they got 460, but it will be very close. Okay, so what is our moment? 456, and we got 474, or your book got 460, that means greater. So it is okay. Then we'll check for deflection. What is the actual deflection? PL cube by this equation. Now this equation you may not memorize, so what you can do for this kind of case, this equation or whatever equation you have to calculate the deflection, you use it. I recommend to use the equation in your book. Whatever for uniformly distributed load, you can use that equation too. Maybe say this equation is derived, you saw it when you saw the deflection design. It is for uniformly distributed load, but still this equation is good enough to get a very good number. Maybe not exactly, but very good number. So if I use this equation, uh, so using the service load, my moment is 313. So m should be based on service load. So we got deflection is this. Now if we use the actual or the capacity is L over 240 or L over 360. L over 240 is giving me 1 inch limit. Now L over 360 will give me lower limit. We will check that, but in this case it is 0.58. So considering L over 240, my deflection is actually less, within the tolerable limit. Now if I use L over 360, what is the value? L means my 20 feet length times 12 divided by 360. My limit is 0.67. So if I use L over 360, my limit is 0.67. How much I am getting? 0.58 using this equation 59, very close. It is okay, yes. Even though deflection is not a structural criteria, but this equation will give us very close number. That should be good. And then so that section 24, 54, 55, which is good for bending, good for deflection also. Now we'll check it for shear. Now shear equation is this. PB CB is problem. If you open the book, you will find there is a superscript V in that section. That means PB CB is not on. PB is 0.9. What is CB? You have to calculate it. You have to calculate CB based on the equation you saw in the shear design section. Okay, they found it is on, which is good. That means if I go back to the shear portion of your book, yeah, this equation, that means the first one was satisfied, so CB is 1. Okay, so for this section we found 0.9, 0.6, 50. AW is TW times D. Everything it gave us 251 keeps. Our share is only 68, so it is way above my requirement. So it is. So this section is this section is good. Now if you are not, even when you say at the beginning, use PB and CB 1 and 1 and compare these two. If there's a huge gap, you do not need to find CB exactly. because we are not mathematician or engineer, scientist. We are engineers, so we know that if a section is way above my requirement, this small value will not affect my result. Okay, but that is for real life. In exam or in national exam like FE exam, P exam, it is better to calculate the exact value. So here we saw that excuse me, whatever section we initially decided for bending, that is good for deflection, and that is good for shear also. Again, to revise you or refresh your mind, this type of table number or this type of value, it changes with the addition of the ASA manual. As we revise, the value changes, so do not memorize it, just memorize the concept. Excuse me. So hopefully you understood how to design a beam or girder. I will wrap up here. Thank you.